Welcome to this first section of our hands-on learning series, where we dive deep into the concepts and the theories that are foundational to electrical engineering. This course maintains the college standard in terms of the topics that we cover, and while we primarily use basic engineering circuit analysis by Irwin and Nelms, we will also reference additional textbooks that cover the same topics. Whether you're just starting out in electrical engineering or looking to reinforce your knowledge, this course is designed to give you practical, real-world experience with every topic that we explore. One reason it's important to understand circuit properties is to avoid damage. In this first scenario, the blue LED burns out instantly because there's no resistor to limit the current. So without understanding circuit properties, too much current flows, destroying the LED. In the second scenario, this is a green LED and it burns out slowly. The resistor is too small, or in this case doesn't exist, allowing more current than the LED can handle over time. But there was less power, so it will burn slow. In this third scenario, the LED stays lit because we use two resistors to bring the current to the correct level. Understanding circuit properties ensures the LED operates safely and reliably. Getting the current right in your circuits isn't just about protecting your components, it's about keeping you safe. If the current is too high, it can cause parts to overheat, fail, or even start a fire. Making a small mistake in your circuit could lead to dangerous results. That's why it's important to understand the basics of electricity and how to use math and formulas to keep everything working safely. By measuring and controlling the current correctly, we can prevent damage and make sure everything runs smoothly. Always measure, calculate, and double-check to protect your circuits and yourself. Here you can see that we have a table representing the system of units. Why is the system of units important? It helps us measure things the same way everywhere. The system of units is important because it lets everyone use the same measurements, no matter where they are in the world. It makes communication clear, and it helps avoid mistakes when we are working with numbers. As an example, 1 mile on your odometer is the same as 1 mile on my odometer, no matter where we are in the world. How funny and interesting it would be if I got pulled over and I told the police officer my mileage is half the speed that his radar gun clocked me at, because I measure mileage differently. And just like 1 mile equaling 1 mile, here on the odometer we can see that 3 miles would also equal 3 miles. The goal in using different units is to maintain simplicity and precision when we are describing something large and small. On the right side of the table, we have the larger values. On the left side of the table, we have the smaller values, and they progressively get larger from left to right, as you can see here. Examples. We say that our phone has 32 gigabytes of storage. If you said your phone has 32 billion bytes, it's confusing and it's hard to compare to other phones. Similar, if I was to use my height, and I am 5'10" tall, but if I was to say 1,803.4 millimeters tall, then it could make it more difficult to understand because that level of precision is not required in that context, or in most situations where my height would be considered. So you can see the units that we use also relates to the context of their use. Sometimes it can be unnecessary to use one unit over the other. Here are 4 real-world electrical measurement examples that you might come across. We have 5 millivolts with the symbol MV, lowercase m, uppercase v, 120 kilowatts with the symbol kW, lowercase k, uppercase w, 0.02 amperes with an uppercase a for the symbol, and 15 nanofarads with the symbol lowercase n, uppercase f. And each of those symbols, you would actually just describe them as MV, KW, A, and NF. Each of these expressions has different measurements, prefixes, units, and symbols. The first element in the expression that I want to take a look at is the measurement element. Now you can just refer to this as measurement, but this tells us how much. So an example for each of these on where the measurement element is would be the numeric value. So we have 5, we've got 120, we have 0.02 here, and then we have 15. So again, this is the measurement element. You can just describe it by saying measurement specifically. Again, this is the numerical value, and it indicates how much of the unit that we have. So this is answering how much. Next, we have the prefix element. This tells us how big or how small compared to the base unit. So this is the prefix element. We just call it prefix. And again, this is how big or how small compared to the base unit. So as an example, you have milli, which is represented by M, or kilo represented by the symbol K. Amp represented by A is the base unit, so no prefix for the unit. The base unit represents a single value right here, like 1 volt or 1 ampere. It's the standard that we compare other measurements to. There's no prefix attached though. If you see just volt or ampere, it means we're talking about one of that unit, and there's no need to mention a prefix. So prefixes like milli or kilo, they modify the base unit. So just remember that. For example, millivolt means 1,000th of a volt, and kilowatt means 1,000 watts, but if there's no prefix, it's the base unit by default like we have for ampere, and not like we see in nanofarads. That is actually modified right here. Lastly, we have the unit element of the expression, and you can just refer to this as unit, and it tells us what we are measuring. So examples are volts with the symbol V, or watts with the symbol W, or amperes in this case with the symbol A. And at the end here, we have farads with the symbol F. So the unit specifies what you are measuring, whether it's voltage, power, current, or capacitance. And these are the characteristics or the actual properties of electricity. We call this unit. What we are measuring here. And again, remember, this is the characteristic or the property of electricity. All right, let's do one last example. Here you can see that we have 4 new expressions: 10 microamperes, 10 microamps, 50 milliohms, 2 gigawatts, and 0.5 farads. So let's pick out our measurement, prefix, and unit. So for our measurement aspect, we have our 10 here, right here. And our measurement aspect on this expression is 50. The measurement here is 2. And the measurement here is 0.5. So that's our measurement, our measure. This tells us how much, once again. And then we have the prefix aspect. So here we have the prefix element, how big or how small. And our prefix is going to be micro here. So our prefix is micro. Our prefix over here is milli. Our prefix down here is giga. And we don't have a prefix here on this last one, so we know that ultimately it's referring to the base unit. It's implying base unit since there is no prefix. So prefix just means how big or small. And finally, here we have the unit. So the unit tells us what we are measuring. The unit tells us what we are measuring. So we are measuring amperes or amps. We are measuring ohms. We are measuring watts. And we are measuring farads. So unit is equal to what we are measuring. And once you get these down, you won't be able to unsee it. It might take a little bit of practice to run several expressions and mark out the measurements, the prefix, and the unit, but you will be able to get this easily enough. Let's start digging into exponents on the system of units table that we have here. So what are exponents? Exponents help us write very large or very small numbers really easily. They show how many zeros to add or where the decimal point goes, rather. I could write, large numbers that just keep going on forever, and we could communicate like this when we're trying to work on circuits if we wanted to. But this would make it really long and painful to work on very small or very large quantities within our circuits, not to mention the amount of room that it would take up. So instead of doing this, we have sort of like nicknames for each of these, or you could think of it as identifiers for the same large or small numbers. For every exponent count that we have here, so the exponent is the small number up to the right, that's the exponent, and then down below to the left, the 10 is what we call base. So we have base, which is why this is referred to as base 10, and then we have our exponent up here at the top. So an example of this that you might have seen before might be something like 2 to the third power. And so 2 to the third power, that would just be the same thing as saying 2, our base number, is multiplied by itself 3 times. This is just saying that 2 is multiplied by itself 3 times. Another example could be, let's say, 3 to the 4th power. That's the same thing as saying 3 multiplied by itself 4 times. For every exponent count, that's how many places the decimal moves. That's an easy way to think of it. If I have 10 to the third, then that's the same thing as saying the decimal place is going to move over to the right. Since the exponent is positive, or a positive value, just think of the decimal place moving to the right 3 place values. So if we start off with our base unit here, imagine we start with our 1, which we know has an implied decimal to the right here. Okay, it's just hidden, but that's implied by the 1. Now we take 1 and we multiply that. So the way that these expressions actually work here is by saying, it's like saying 1 times 10 to the third, or 1 times 10 to the 6th, okay? And on we go. So when we say 10 to the third, what we're actually saying is the decimal place moves from the base unit, it moves to the right 3 place values. So if we have our base unit and we say our decimal is going to move 3 places to the right, then we add a 0 every time it moves. So we add 1 0 because it's going to move 1 place to the right, 2 places to the right, and 3 places to the right, which is the same thing as just saying 1,000. Equally, 10 raised to the power of negative 3, 10 raised to the power of negative 3, the exponent is negative now, so we move the decimal point 3 places to the left. And this makes the number smaller. So again, negative exponent means move to the left. So I'll just write this up here. We'll say positive exponent exponent, if you could read that. Means move decimal right. And negative exponent means move decimal left. So if we have 10 to the negative third power, we are saying that the exponent is negative. We move the decimal point 3 places to the left. We start with our base unit, which is the 1 point. And we start here, and then we move it to the left 3 places. So 1, 2, I'm going to put another 0, and 3. So now our decimal place has moved from here, 1 place, 2 places, 3 places, and now it resides here. So we are left with 0.001, but the standard of writing this expression is by placing a 0 to the left of the decimal place. Anytime the decimal is out to the left like this by itself, and we don't have a significant figure or a significant number to put out here, then we just write a 0 out there. And this is just a way of verifying the final value that we have here, okay? Because it could just be said that something's missing. Maybe a significant number is missing. So we want to make sure we fill this 0 out here to the left as well. On more exponent explanation, we measure things like voltage, current, or resistance in circuits. Exponents tell us where the decimal point is going to go. For example, if you have 5 millivolts, which we have written up here, and I will include the symbol millivolts here, that is 5 times 10 to the negative third volts, or 0.005 volts. So we can look down here at our table, and we're referring to milli. So we have milli right here, and we know that's 10 to the negative third, and we know that our significant value or our measurement is 5. So 5, we're going to go down to our base unit. It's going to substitute for 1 here. So we're going to have our 5, and we are going to multiply that by 10 to the negative third. The exponent moves the decimal to the correct place value location, making it easier to work with these values. So we know negative 3. So negative 3, because it's negative, because our exponent is negative, it means move the decimal to the left, and 3 is the amount of locations or positions it's going to move to the left. So if we have our 5, and we know the starting point is originally right here, we're going to move it once. That's 1 place. And then second place, we're going to add a 0. And then finally the third place, we're going to add another 0, and we know it ends up right here. So this equals 0.005. And then we know that because of confusion that can occur without a figure out here to the left of the decimal, just to add some verification, the standard is to add a 0 out on the left there. So that's our answer. So 0.005 volts. And so now we're getting into conversion, and that's exactly what these exponents help us to do. So we had 5 millivolts, and that's the same thing as saying 0.005 volts, or a fraction of a volt. So this is crucial to understand, since a component like, say, an integrated circuit can have 50 million transistors, 50 million. So we need to be able to work with really small numbers like this that can also have a very big impact. And these types of chips are everywhere around us in devices. So when we see something like this exponent where 10 is raised to a specific power, that means that we multiply our 10 by that power. All right, so we're having fun here. We're on a roll. Let's keep going with this so you can see the progression here with the base 10 to a power. when you see something like 10 raised to the power of 0, what does that mean? 10 to the power of 0. You might think 10 to the power of 0 would equal 0, and that would make sense. In math, the standard is that 10 to the power of 0 or anything to the power of 0 is actually 1. So this is where we actually get this 1 point here, because this is actually saying 10 to the 0, okay? 10 to the 0. So don't blame me. I didn't make this up or come up with it, but other people that are really smart and smarter than me came up with this. So 10 to the power of 0. Sometimes you will also see in documentation or written out with the caret symbol here, where this is equal to saying 10 to the power of 0. Okay, so just so you realize that sometimes you might see some documentation like this with a caret, and it's probably because their software didn't allow them to raise this number to the power position. This just means that we are multiplying 10 by 0. That gives us 1. Now let's move on to, let's say, 10 to the power of 1. What does that mean? So 10 to the power of 1, this can mean multiply 10 by itself one time. So this gives us 10. And then if you keep walking up the exponents or increasing the exponents, we would say 10 to the power of 2, which would be 10 times 10. And this is going to equal 100. Or 10 to the power of 3, this is going to equal 10 times 10. It's the same thing as saying 10 times 10 times 10 equals, I'm running out of space, 1,000. So hopefully this helps you to see what the actual calculation looks like for each of these identifiers like we were talking about earlier. Yeah, we could write these really long or really short numbers, but it's much easier to manage if we have a more compact way to say the same thing. Now let's discuss the other side of the system of units here that we have, and that's the negative exponents. So what about when we see a negative exponent? So we see 10 raised to a negative 1, let's say. If we have 10 to the negative 1, what we are actually saying is we are taking our base unit and multiplying it by a tenth. So 1 over 10. And so if you work out the math on this, if I was to be a little verbose about what each of these actually mean, this 1 point is the same thing as saying 1 over 1. Because remember, any integer, like 2, is the same thing as saying in fraction form 2 over 1. Okay? Same thing as if we had 7 as an integer. It's the same thing in a fraction form as saying 7 over 1. Okay? So we have our 1 point, or our base unit, in the numerator here on the top, and we have our 1 in the denominator, and we're going to multiply this by 1 over 10, which is our 10 to the negative 1. This is what that expresses here. And so what we end up with here is a 0.1. And the way that happens is because 1 times 1 is 1. So then you get the 1 in the numerator in the top. And then 10 times 1 is 10. And then 1 divided by 10 is what's going to give you 0.1. So that's your answer there. Let's try 10 to the negative 2, which is saying 1 over 10 times 1 over 10, which is equal to 0.01. Because you're going to have 1 times 1, which equals 1. 10 times 10 is 100. And then 1 divided by 100 is going to be 0.01. Let's finish off with one more example here. Let's say 10 to the third power is the same as saying 1 point times 1/10 multiplied by 1/10 multiplied by 1/10. And so this is going to give you 0.001. So you can see immediately -3 in the exponent. If we start with our base unit where the decimal is to the right, then we count places 3 times and to the left. 1. So 1 place, 2 places, 3 places, and then the decimal sits out to the left. And then we have our 0 out in the front here. Hopefully this helps you to understand a little bit about how exponents work and how base 10 works in regard to the system of units, because we're going to be using this all the time, because this really is speaking the language of the calculations in our circuits. Let's work on a few electrical examples using what we've learned. If we have 2 microamps, and here is my symbol for microamps in parentheses here, and let's say that we look down here at our table of units, our table for the system of units, and we find micro. Micro's right here, and it's 10 to the -6. So what we are saying by 2 microamps is we're saying 2, remember, times, and then because it's negative, it's going to be 1/10 6 times. 1/10, so it's 1. Here's 2. We have 1/10 3 times, 1/10 4 times, 1/10 5 times, and 1/10 6 times. Okay. So when you work all this out, just like we did in the past, we would say 2 times 1 is 2. 2 times 1 is 2. 2 times 1 is 2. So we already know in the top we're going to have, or the numerator, we're going to have a 2. Now 1 times 10 is 10. 10 times 10 is 100. So we have how many? 1, 2, 3, 4, 5, 6. 6 of those, so that we know that we're going to have 6 zeros. 1, 2, 3. 1, 2, 3. So there's 6 zeros there, okay? So 1 million. So now we can divide 2 by 1 million, and this is going to give us 0.0000002, okay? If you sort of check the decimal movement here, we started out with 2 point. So let's imagine the starting point was here with our decimal, and then it's moved. We're saying we need 10 to the 6, -6, so we need 6 places that it needs to move. So we go 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places. Let's do another example here using some electrical values. Let's say we have a scenario where we have 3 kilowatts. 3 kilowatts. And our symbol for this is going to be lowercase k, uppercase w. And so 3 kilowatts. So we know that our starting measurement is 3, so that takes the place of our base unit. So basically we have 3 point here, or 3 decimal. And then kilo, where is kilo? Kilo is over here, and it's 10 to the 3rd. So this is the same thing as saying 10 to the 3rd times 10 to the 3rd. Okay. And so when you work this out, this is going to end up being 3,000 watts. So 3 kilowatts is the same thing as 3,000 watts. So we are working on unit conversion right now, just so you realize that we're going from kilowatts to watts. We're looking at what does the measurement mean with this level of exponent in comparison to what it means in this level of exponent. So another way you can think of this as you can multiply, which you may have already figured this out, you can multiply your significant value, your measurement there, by 10 to the 3rd, which is the same thing as saying 1,000. So you can just multiply by 1,000 and you're going to get 3,000 watts. All right, we have another example here. Let's work with nanofarads. let's say we have 10 nanofarads. And then our symbol would be our n, lowercase n, uppercase f. This is going to be a long one, so if we say nanofarads, we look down here from our base unit. To the left, we have nano right down here, all the way down here. So this is saying the same thing as 10 times, or 10.1 times 10 to the negative 9. So it's like saying 1 over 10 9 times. So let's write this out. It's 2 times, 3 times, 4 times. So here is 5. Yeah, 1, 2, 3, 4, 5. 6 of them. 7 of them. 8 of them. 9 of them. And 10 of them. So you get the idea. So, oh, actually, nano is negative 9. So look at, I'm already making a mistake here. So if I get rid of this last one, let's make sure we've got 9 here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to do exactly the same way. In the numerator, you're going to multiply 10 times 1 times 1 times 1 times 1 is just 10. So we have 10 in our numerator. And then to the negative 9, well, that's the same thing. We could walk through all these and count the zeros, but that's the same thing as if we take our base unit, remember, which starts as 1 point, and we just move it over 9 times. Well, if we know that our base unit is 1, this counts as a place value, so that's 1 place value, and then we just need 8 more zeros. So it's 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then the decimal lands at the end there. And then we would actually, well, I can delete that just so you can see it. It's cleaner up. It's cleaner here. And so let's just verify that that's right. So then we've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yep, that's right. And then according to the standard, we put our 0 out front. So that is 10 nanofarads, or 10 nanofarads. So this is what 10 nanofarads looks like down here. Okay, we have one last scenario here. Let's do gigahertz. If you have 7 gigahertz, 7 gigahertz, and our symbol, uppercase G, uppercase H, and lowercase z. And we are going to use an uppercase G, an uppercase H, and a lowercase z. So what is 7 gigahertz? We start off with our base unit. So our significant measure is 7 here. So 7 will be substituted for our 1. So we already know that. So we've got 7. And it's going to be multiplied by giga. Where is giga down here? So we've got kilo, 10 to the 3rd, mega, 10 to the 6th, and giga, 10 to the 9th. So then we've got 10 to the 9th here. So what we can do is just count out 9 spaces here, or 9 place values, starting from here. So we go 1 place value, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So let's just verify that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that is 7 billion hertz right there. So if we were to add commas like we're used to seeing for long numbers so that we can break it into sections of 3, we would see, wait, let's do it backwards. There's 3, 6, 9. Yep. So we would have comma here. Now we'd have 3, comma here, and there. And that's our answer. I want to do a few more examples here just so we can really drive this idea of conversion home and how we do it. So in these examples, we are going to convert from smaller to larger units, and we will do a few examples like that, and then we will do several other examples where we convert from larger units to small units, so you can kind of see the pattern here. In this example, let's convert millivolts to volts. So we go down here to our system of units table, we find millivolts, we're going to convert from millivolts to volts. And so remember, when there is no prefix like milli, then we know that we're converting back to the base unit here, when all you see is the unit type, which would be volts. In this scenario, let us convert, let's say 750 millivolts and let's use our symbol for lowercase m for milli and uppercase V for millivolts, or for volts rather. And the first thing that we want to do is identify the conversion, which we did. We're going from milli to our base unit. And so let's look at that conversion factor. So I actually like to write this out sometimes. So my conversion factor is equal to 1 millivolt. So 1 millivolt is equal to, let's keep our symbol in here actually, is equal to 0.001 volts. So we already know this based off of what we've looked at in the last examples after we run the calculations with multiplying the initial value, or our base unit value, times 1 over 10 times 1 over 10 times 1 over 10. So just to show you once more, it's like we say we take our base unit value with our decimal, and it's the same thing in a fraction form as saying 1 over 1, and then we multiply it. Since we are dealing with a negative exponent, we multiply it times 1 over 10, as many exponents as are there. So like in this case, milli, it's -3. So we're going to multiply by 1 over 10 3 times here, okay? So instead of writing all this out every time, we already intuitively know now that when we see that -3 in the exponent, that we are just simply taking our base unit, which we already know it's implied that it has a decimal place to the right, and then we just count to the left 3 places. So we go left, we move left because of the negative exponent, and then the number of spaces or locations or place values, however you want to think about it, that we move is aligned with the number in the exponent here. So it's like saying 1 place, 2 place, 3 place. So we just fill the zeros in for here, just like that. And then we put that 0 out front. So we're left with 0.0001. So we already know, if we write out every bit of the calculation, we know how it works now. So intuitively, we can run these calculations like this from now on, moving forward. So we know our conversion factor is 0.001 volts. Now all we do is multiply our significant value, our significant measure here, by our conversion factor, which is 0.001. So we can just multiply that. So we would say 750 times 0.001, and then we always want to write our units and our prefixes over here in a fraction form, m over v. So v over m over v. The one that we want to end with, the unit that we want to end with, is in the numerator right here. So then our final value is 0.75 volts if you run that on a calculator. In this next example, let's convert microfarads to farads. Let's start with a value to convert. We can try 3 microfarads. And include our symbol. The pronunciation on this symbol for micro is mu, M-U, in case I didn't say that before. I have a habit of just saying micro or micron. And the first thing we want to do is identify the conversion factor. So what's the conversion factor? And we've already worked through this several times, so we'll do it again. So we go down to our system of units table that we have down here. We can locate micro here, which is 10 to the negative 6. We see the negative exponent, which means that our decimal is going to move from the right to the left. And then negative 6. It's going to move negative 6, or 6 places to the left, rather. So we start with our significant value, or our measure right here, which is 3. And remember, 3 just gets substituted for our base unit. So then it's as if we say 3 point. It's as if we start with 3 and then our decimals here off to the right. And we are going to count 6 places over to the left. So instead of drawing underneath here like I've done before in the past, we're just going to try to count it. So we already know that our significant number right here counts as 1. So that's 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places. And then we know since we are going to the left, our decimal is going to be right out in front here. And then according to standard, we will just put this 0 out here. And then let me clean up the answer here. Just get rid of this and the initial decimal. And there is your answer. So this is converting 3 microfarads to farads. And just to run the calculation on this, since 1 microfarad right here is equal to, let's say 1 microfarad. Just to be clear, 1 microfarad is equal to 0, 0, 0, 0, so 5 zeros, and then our 1, right? That's our conversion factor. So we multiply our 3 microfarads by this 0.00001. So the equation actually looks like 3 times 0.0000001. Final answer, which is right here, 0.000003 farads. So again, we're moving from a smaller to a larger unit here. We've moved from our micro to our base unit, which is a larger unit than micro. Here is our final example, converting a smaller value to a larger value. Let's convert 500 nanoamperes to amperes or amps. So we start out with our measurements, which is 500, and our prefix, nano, and amperes, our unit. And include our symbol here. All right, so our significant measurement is right here, it's 500. That's going to be substituted for our base unit here. And let's identify the conversion factor. So what is our conversion factor? Well, we already know if we come down here to our table, we have our base unit, we have milli, we have micro, we have nano. Nano has an exponent that is negative, so we already know that our decimal is going to move to the left. Decimal is going to move to the left because it's negative. And we know how many place values or locations it's going to move to the left. what we are saying is that 1 nanoampere is equal to, if we run all the calculation, remember it's the same thing as saying we have our base unit, then we move our decimal 9 places. So 1, 2, 3, 4, 5, 6, 7, 8, and 9, and then our decimal sits right here for the final answer. So to rewrite this, we have our 0 up front per the standard, and then we're going to have 8 zeros. 1, 2, 3, 4, 5, 6, 7, and 8, and then our significant measurement there. So this is our conversion factor. So all we're going to do is multiply our significant measurement 500 by this conversion factor. So here's our conversion factor right here. This is the same thing as our conversion factor up there, instead of rewriting all those zeros up here. The equation looks like 500 times 0, 1, 2, 3, 4, 5, 6, 7, 8, and then our 1. Okay. And this is going to produce 0.00005. And so there is our conversion. And this is now converted to amperes because we were moving from nano to the base unit. So now it is in amps. And you can see this is a fraction of an amp. It's only a small piece of the whole amp. Okay, let's switch it up and convert from a larger unit to a smaller unit. So let's convert from 5 kilowatts to watts. So if we look at our table for the system of units, we can see that we're moving from kilowatts right here to our base unit. Since watts leaves the prefix out, that's how we know that we're going to the base unit. All right. So our value to convert is 5 kilowatts. So let's look at this for a second. If we look at kilo, 10 to the third, and we take our base unit, which we start out with the 1 with the decimal to the right, we already know 10 to the third, so it's a positive exponent, so that means we're going to move to the right. And then 3 means we're going to move 3 place values. So we could actually say 1, 2, and 3. And so it's like the decimal is moving from 1, 2 to 3 to here. So the conversion factor between here is 1,000. So if we come back up here, now that we've identified the conversion factor, so we know that 1 kilowatt is the same thing as 1,000 watts. Now let's multiply the final equation here, 5 kilowatts times 1,000 watts. The unit that we're going to keep always goes in the numerator, and the unit that we're converting from is in the denominator here. So our final value for our conversion is going to be 5,000 watts. And that's our answer. Okay, next, let's convert 8 megahertz to hertz. So let's identify the scale that we're moving in. So we're moving from a large unit to a smaller unit. So if we move from, say, megahertz, whereas mega is right here, 10 to the 6th, and we want to convert to hertz, well, since there's no prefix, that tells us or implies that we are going to the base unit. So we will end down here at the base unit in our conversion. So we are going from large to small. Okay. So let's convert 8 megahertz. Okay. And then our symbol right there. The first thing we want to do is identify the conversion. So what is the base unit equal to when we have 1 megahertz? So 1 megahertz, and I will just do the symbol here. So 1 megahertz is equal to, well, it says right here 10 to the 6th, so we know that if we start from the base unit with the implied decimal place on the right, and we increase it, since it's positive, since the exponent is positive here, we know that it goes to the right, and we know that it goes 6 place values. So we're going to have 1, 2, 3, 4, 5, and 6, okay? So 1 megahertz is equal to 1 million hertz. We've identified the conversion factor. Let's multiply the value. So we have our measurement right here, which is 8. We are going to take 8 and multiply it by 1 million. And this will give us 8 million hertz. Typically, you'd put this to the right, our symbol, but I ran out of space there. This conversion takes us from the larger unit, which is mega, to the smaller unit, which is our base unit, identified as hertz. And this is the answer. Okay, let's do another conversion from a large unit to a smaller unit. How about we work from giga to, let's say, kilo? Giga to kilo. I like writing out little arrows and signs to myself because it helps me to keep track of what the objective is. A lot of the most common mistakes in advanced math relate to, actually, believe it or not, arithmetic and algebra. So I like to try to keep track this way. So the value that we're going to convert, let's say we have 0.2 gigawatts. And here is our symbol or identifier. Okay. Now we want to identify the conversion. So what is the conversion? The distance between here, if we think about our conversion, we've calculated this many times over. Remember, if we start from the base unit, it's as though there is an implied invisible decimal right there. If we go from base unit to kilo, that is adding 3 zeros. That's what that means. It's a positive exponent, so it means we're going to move the decimal to the right and then 3 spaces. And then if you notice, the same thing applies from 10 to the 3rd to 10 to the 6th. Oh, what do we have? That's a positive 6, and it is 3 place values. So we can see the conversion again. Between our base unit and kilo is 1,000. Between kilo and mega is 1,000. Between mega and giga is 1,000, or the 3 spaces here. So the shorthand is, we could just say, okay, well, basically we have 9 zeros from base unit to giga, but we don't want to make a mistake here. So we're not going from giga all the way down to the base unit. We're actually only going from giga to kilo. And this is why I like to draw little arrows and things that are just reminders to myself about the objective itself. So we actually only need to go 6 place values here, right? From 10 to the 3rd, 10 to the 9th, or 10 to the 9th to 10 to the 3rd. So our problem will look something like this. Here is our significant value, or our measurement, 0.2. And then we are going to multiply that by, you probably already guessed it, 1 million. And so the unit that we're going to keep is kilowatt. That's what we want in our answer, so that goes in the numerator. And in the denominator, we were given gigawatt, so that will go in the denominator. And our answer here, if we multiply this, we get, you probably guessed it, 200,000 kilowatts. And that's our answer.